The only reason Eric's not giving this talk is because he just gave the previous talk. So he was one of the co-authors of this. He helped advise two very talented undergrads that did a lot of the experimental work here. So this talk is about multi-ported memories for FPGAs. By a multi-ported memory, I mean a memory that has more than 2 ports. There's lots of things you can do with these in systems on FPGAs for communication and storage between multiple components. The trick is FPGAs come with hard built-in block RAMs, but those typically have only 2 ports. So if you need a memory with more than 2 ports, you have to build it yourself, either by combining multiple block RAMs or using pure random logic or some clever combination of the 2 things. So what I want to go through is some of the different ways that you could do this. And I'm going to use this running example, which I think is the simplest multi-ported memory we can think about. Something, a memory with 2 writes and 2 write ports and 2 read ports. So how can we build this thing? What are some options? One option is you could build it the hard way out of pure logic elements and, let's say, individual registers. And previous work has shown that you can do this, but it doesn't run very fast, and it actually consumes quite a bit of logic as you scale this up to larger memories. Another possibility is through replication. So this shows 2 replicated block RAMs. Each would have a complete copy of the storage. So a write would be broadcast to all of these memories. And this is a good way to support any number of read ports, but this trick only works for a single write port. So while it works fairly well, it's not a real solution for what we're looking for. Another possibility is banking. If I have 2 separate block RAM banks, I can have individual write ports mapped to each bank and reads also mapped to those banks. However, now the data is fragmented, so it's up to the enclosing design to steer reads and writes to the right places. So this is also not a good solution for what we're looking for. An example of a good solution is multipumping. So this is the idea that from the outside world, you look like you have some number of write ports and read ports. Internally, you have a simpler memory with fewer read and write ports that you're clocking at some multiple of the external clock signal. So for example, here I could use a single 2-ported block RAM to provide 2 write and 2 read ports by clocking it at twice the frequency of the external clock. So this works fairly well. There's no fragmentation to worry about, no particular steering of reads and writes. However, it does run at some division of your actual clock frequency. So there's a frequency cost to the design. That was the stage when we came up with the live value table design in FPGA 10. To remind you quickly about that design, again, we want to build a 2 write, 2 read memory. We'll do this by taking a banked design, so 2 separate block RAM banks. Actually, each one is replicated to provide 1 write and 2 reads. Okay? And what we'll do is we need multiplexing to steer the read ports so they can read from either of those banks. And the trick is a skinny table called the live value table, which remembers which of the block RAMs was most recently written for a given location, and will steer each read port to the correct write bank. So that's the basic idea of the live value table design. And it gives you a pretty good frequency win compared to the pure logic approach that I showed you. This goes a lot faster. However, it's not perfect. It uses a lot of logic to build that live value table, the table itself, for memories that are very deep, memories with a lot of locations. And also the logic required for all the multiplexing can also add up, as I'll show you. So this motivated us to try thinking of other possible designs, and we tried this XOR design. So a little bit of background about XOR, for anyone who forgets. If you have A XOR 0, that gives you A back. If you have B XOR B, you get 0. If I combine these 2 things, that means if you have A XOR B XOR B, you'll get A back. You get the original value. And that's the property we're going to exploit. So the question is, how can we use that to build better multi-ported memories? And the intuition is we want to avoid the logic required for that live value table and for all the multiplexing at the output. So I'm going to attempt to walk you through this design of a 2-write, 2-read, and we're going to kind of design it backwards from the output towards the input. So we want reading, a read port, to be only an XOR. So I've shown that here. And we need 2 block RAMs for this to be interesting, and we're going to focus on just a single location, so shown in dark blue. And at the bottom, we'll assume this block RAM has some old stale value that we don't care about anymore. And what we need to have stored a proper new value, A, let's say, is to store A XOR that old value in the corresponding location in the other block RAM. And this way, when I read, I only have to do an XOR of those 2 locations. So just to check the logic here, that would give us A XOR old XORed with the old value. So again, A XOR old would give us A back, right? So this is how we can recover A from the mix of those values. So now how do I get to that nice position? So I need a write port. In order to write, what I need to do is read that old stale value and XOR it with the new value I'm trying to write. So I want to store A XOR that old value in the block RAM which is allocated to that particular write port. Okay, and now hopefully you remember that now if I tried to read that location, I'd get A XOR old, which would give me A back. Okay, so far so good. Next, you might notice that this is cheating, right? So I have one port kind of used for 2 different things. I might want to read some different location at the output here than I'm writing, right? So really I need 2 ports for that. So I'm going to need to do more replication, and while I'm at it, I'm going to add more support for another write port. So these block RAMs that I've added on the left are replicated copies, and they're only for the purpose of providing values for write ports to read in order to do their writing. So again, for a particular location, if the first write port writes the value A, I'd be storing A XOR old 1, that particular value. And if the other port writes the value B in a different location, I'd be storing B XOR some other old value in a different location. And again, hopefully you agree I could now read either of those locations, XOR the values of those locations together, and get either A or B out. So the final step is I need to add support for my second read port. And this is fairly easily accomplished just by doing a little more replication. So I'm going to add another column of replicated block RAMs, and I hook this up to another XOR to provide another read port. Okay. So there's something to notice here. There's 2 little problems or challenges that I have to tell you about. One is the astute audience member might have noticed then that it takes reading in order to do writing. And so that takes 2 cycles. And this is a bit of a problem. I don't want the design to be capable of only a write every other cycle. I want to be able to write every cycle. So to do this, we had to, well, first I'm illustrating it. So to do a write, I first have to read. That takes 1 clock cycle. And then I can finally store the value in a second cycle. So in order to get around this, we actually did the proper pipelining to allow writing every cycle. But I'm not going to show you the details of that because it would take too long. The second challenge is, what if you try to read 1 cycle after you've written that same location? So again, it takes 2 cycles to accomplish a write. I don't want to have this memory be different than all my other memories. This one takes 2 cycles for a write to be performed. I'd like it to appear to be performed in 1 cycle. So again, to illustrate, if I'm in the first cycle of my write and the read shows up, I might get the wrong value. So to support this, we add forwarding, okay, to be able to forward from the input to the read. And again, I'm not going to show the details of this because I won't have enough time. So that's the basic idea of how it's constructed. We've generalized this so we can actually build a memory of any number of read or write ports. To show you quickly through the generalization, what this has is a row of block RAMs for every write port. Okay. And this first wide column is for supporting however many different write ports you have. So it's m-1 block RAMs wide if you have m different write ports. It's for the purpose of providing read values for the purpose of writing. Okay, that's what those are all for. And the other columns are one column per read port for the purpose of providing read values. Okay, so that's a quick run through of how the block RAMs are used. How does this compare now with the live value table approach, which was the best previous known approach? Quickly, our comparison methodology. So we did all this on Quartus 10.0, targeting a Stratix 4. We did speed optimization, favoring speed over area. Everything in the paper and here is averaged over 10 seeds. We report area as the total equivalent area. So this is using the number kindly provided by Vaughn, which tells us how many ALMs worth of area a M9K takes. And we measure a pretty big design space. So memories from 32 up to 8K deep, and memories with varying numbers of ports. So 2 write, 4 read, 4 write, 8 read, 8 write, 16 read. And first I'd like to show you a picture, because those are easier to digest. And this picture really sums up how the two compare. So on the left is the live value table design, on the right is the XOR design. The green columns are the in-use block RAMs, and the blue blobs are the in-use ALMs. And just by eyeballing it, you can see XOR does use more block RAMs. The columns are taller. And you can also see live value table uses significantly more ALMs. So this is for a fairly large design, 8K deep, 2 write, 4 read. And you can see it's actually taking a fairly significant chunk of the chip. But the thing to note is, again, these are implementing both the exact same thing from the user's point of view. And there's a significant resource diversity here. So a lot of choice for a designer which one they'd want to use depending on the scenario. Just to look at some more detailed performance results, so we measured speed versus total equivalent ALMs. So Fmax is on the y-axis, higher is faster, and total equivalent area is on the x-axis, smaller is moving towards the left. And keep in mind, this is a log scale. And so eyeballing it, you could see live value tables in red, XORs in blue. The little numbers are the depth of the different memories that we tried, and this is for 2 write, 4 read. Eyeballing it, you could see they're fairly comparable. If we look as memories start to get large, the XOR design starts to get a little bit faster and actually takes significantly fewer, significantly less total equivalent area. So it's almost half the size and about 15% faster than the equivalent live value table design. And you might also notice there's this annoying cat anomaly in this work here as well. So we found the 1024 entry design actually runs a fair bit faster than the 512 entry design. Although we gave this to Altera and they assure us that this is fixed in the current version of Quartus, although we haven't got to confirm it yet. So to try to make a more thorough comparison, we tried a whole bunch of different memory depths, XOR versus LVT, and which is better depending on what feature you care about most. So if you care about minimizing your usage of block RAMs, the live value table design tends to be best. Whether you care about minimizing the delay of the circuit or care about minimizing the number of ALMs used. So again, eyeballing the table, you can see that it does depend a little bit on what your features are and what you care about, which design you should use. And just to stare at this same table for 3 different designs, so 2 write, 4 read, 4 write, 8 read, 8 write, 16 read, there's a few fairly rough trends here, so I'll highlight them. If you really care about minimizing block RAMs, you always want to use the live value table design. So that seems fairly clear. Or if you want to build something which is 128 entries or less, then you probably also want to use the live value table design. And otherwise, the XOR design seems to be the best design to use to minimize delay or ALM usage for designs that are 256 elements or larger. So that sums up most of the design space. So to conclude, we think this would make a pretty interesting library or generator to help the user navigate this space. Ideally, it might even take into account what are the constraints of the enclosing design to choose which is the best implementation to slip in. And we're interested in doing future work on this, exploring how we can exploit true dual port mode, maybe consider designs that allow a little bit of stalling as long as it's not too frequent. We might consider power, and finally, of course, we'd like to map this to Xilinx or maybe other FPGAs and see how it behaves there. And that is all. Thank you. Marcel?
Yeah, you may have missed something, but so the reason this works is because you have the same value in two memories, then you XOR something to the old value, and then you can XOR the two things back and get the new value.
Yeah, so you have to think about, there's some initial starting state where the whole memory is full of stuff you don't care about, and your very first write will XOR this new value you do care about with the old thing you don't care about, and store that in one of the replicants, and that's kind of how you get the thing off the ground.
So but the two memories have like the same thing to start, or?
No, they don't have to, right? So one is garbage, and the other is new stuff, XOR that old garbage.
So when you XOR kind of the different garbage, like some garbage with new stuff XORed with some other garbage, you XOR that together to get the output?
No, so I should go back to the picture.
You're only XORing one garbage.
Sorry.
You're only XORing one of the garbages.
But when you read it out later.
You're XORing garbage with good stuff.
No, let's go here. Yeah, so when the memory starts up, because that's the easier scenario to think about, so this is some initial crap. There's also initial crap here, but I'm not going to read that, right? It's okay if they're different.
Right.
So I'm going to XOR the new value I care about with the old thing, and that goes in the new location. Maybe what you're...
When you read it out.
And now, so if you believe I have a way to get to this situation, right? Now when I read, I'll just XOR these two things together. And because this has a copy of the old thing, when I XOR this all together, those two things kind of cancel each other out, and I end up with the value I cared about. It's a bit of a leap, I guess. Sorry, Jonathan.
I was just wondering if the forwarding path for that you put in to make the writes not wait for a cycle to show up as read, did that show up as part of the critical paths, or was it not?
The critical path.
Limited use speed.
Let's see. Yeah, should probably know what the critical path is off the top of my head. I don't think it was, but yeah, I'd have to check to know for sure. And if Eric doesn't remember either, I don't feel so bad, but that's something we should probably know.
Refresh your memory on that.
Okay, any other questions?
There's no pizza yet, so you might as well ask questions.
I don't have much knowledge about FPGA, but I really like this idea because I think the key point of this design is the equation that A XOR B and XOR B X to A. And this question is not very related to your implementation. It's just I'm curious, I'm interested because I noticed that in last year's International Symposium on Microarchitecture, the Micro Conference, there are two papers also use this equation.
Yeah.
So
great minds think alike. So that was
different
the.
with cache. So I'm wondering.
So I just saw that yesterday. Professor Michel Vos emailed it to me. So it was Mikko Lepaski had two papers using XOR. One for a register file.
Memory control
although he was doing it kind of differently than we are, but but that was like the closest related work that's appeared. We actually found precious little when we were searching for related work on XOR. It is used in RAID 5, is it?
Yeah, and some of the.
Yeah, it's used in
yeah.
RAID 5 to spread data across multiple hard drives, but that was the most relevant thing we could find.
I think network coding.
And
Yes.
Network
Yeah.
coding also do that.
Yeah.
Yeah, it's, the other one is using.
like it's,
the
yeah,
router.
like we're definitely not, it's not the first to use XOR in building a system, but we were looking for memories and storage, and
Yeah.
the RAID seemed the
I
most.
think in old days when people paint the mouse on the screen.
Yeah, it's used for the cursor, yeah.
So really, I'm wondering why people will begin to interested in this equation recently.
Oh, like, so where did this come from? When we were touring around talking about the live value table, a couple people suggested they had heard rumors of a magical XOR design for doing this kind of thing. Although no one could actually point us to evidence of a design, web searches didn't lead to much. So there was lots of people chatting about it, and it seemed something that had been done before, but we couldn't find direct evidence that it had. So we did kind of have to figure out how to do it from scratch, more or less, and work out these hairier details about forwarding and pipelining to get it to work. Now, how Miko's group happened to come across the same thing almost at the same time, I don't know. I'll have to talk to him about it. Vaughn?
Can you walk me through, do you have another diagram later on where you show why you have n-1 columns for writing, I think?
Oh,
The old guys.
that
I
was.
keep thinking it should be m, so.
No, it's,
Walk
if
me
you think
through.
about it, where did I show that?
I'm sure you're right, I just don't.
Yep.
It's not registering in my brain.
It's because, so remember, so this group is for providing read values for the
Yeah.
ports, because you need to write, you need to read when you write. So if you think about it, each of these each write port needs to read all the other write ports storage.
So what
So
do
you
I
need
need
one
m of them?
for every other.
Don't I need m of them then? Don't I need one for myself as well? Like,
No, because you don't read your own location, you only read everyone else's. You overwrite your location.
so one guy is overwriting and everybody else is XORing. No.
Everyone else is providing read values, and you're overwriting your own location. So you
I
don't
see.
need to read for yourself.
Okay.
Yes?
So as you are ping-ponging through two different memories, you somehow need to remember which one, right? So is there extra state?
What do you mean ping, sorry, you're talking about the XOR design?
Yes, because.
So the nice thing about the XOR design
you
is,
have to,
sorry?
so when you write a new value, right, so you have to read the old value from the other bank, right?
Yeah,
So, but, somehow you need to know, is it upper bank or lower
no,
bank, right?
so there's this, I guess this design is, the nice thing about it is, the live value table remembers which bank something was written to. This one does not do that remembering, and that's why there's no output multiplexing, at least at the first level. So this design gets away from having to remember what was written where by just blindly XORing everything together. So that's why when you write, you're going to read all the other values and XOR them all together and store that. And this way, when you read, you're oblivious of which bank to get it from. You read from all the banks, XOR it all together, and that gives you that recovers the original result.
Okay.
So, this is a question that's probably trivial, but what happens if you write the same address simultaneously?
Yeah, so we don't support that, and a lot of other.
That's
so
like
we-
standard not supported, right?
Yeah, so across all the designs we implemented anyway, we don't support reading and writing multiple write ports writing the same location at the same time.
In this case, you would get some sort of,
Some kind of garbage.
Right?
And you might get different garbage than you would with our live value table memory, let's say. So that's a complication. But a lot of designs don't support that, and so yeah.
Can you make the design more efficient if, let's say hypothetically, the block RAM supported an operation natively where instead of writing you wrote a word to the block RAM and that word replaced the old word, that word instead was XOR to the previous word. So let's say you just at the physical level, rather than writing a new value, you automatically run the XOR.
If a block RAM provided sort of XOR equals,
That's right.
if it would update a location by XORing with what you gave it. That's a bit of a brain buster. I'd have to go think about it.
Would you be
get some efficiency from that, but probably maybe not quite as much as you think, because that internally to the RAM, you're forcing a read modify write cycle.
Right.
That you can avoid. You can do all the XORing inside, so you sort of hardened your XOR, but.
Yeah,
it's
like you
not
save the
quite as-
XOR logic, I don't know if
Yeah,
you
you
save
save that, but you move a read and then a write cycle inside the RAM timing logic, which doesn't actually gain you that much, but you would gain from hardening the XOR.
But do you gain from being able to eliminate some of the n-1 column fees?
I don't think so.
You still have to read everybody else.
I think, unfortunately, I think the only thing that would help that is more ports on the block RAMs. All right,
Okay.
so pizza's here, thank you.
Okay, pizza sponsor.